Welcome everyone to this NPTEL course on topological phases of matter, and this course is 12 weeks and 13 hours, and in this course I will give a almost a complete view about topological phases of matter, starting from very fundamentals of topology, which is more of a mathematical thing, going all the way to experiments. And at the outset, let me say that this course is designed for condensed matter, mainly for quantum condensed matter, but in the first 2-3 lectures, first 2-3 chapters will be general for all, even for classical condensed matter or even beyond it. Those even who are working on gauge theory would also benefit from it. And so, my name is Tanmay Das, and I am a professor in the Department of Physics at IISc, Indian Institute of Science, Bengaluru. And for this particular course, my two PhD students Rahul Satapathy and Gurpreet Singh, they will be assisting me with this course, preparing the lectures as well as gradings and so on. So, as I said, who will benefit from this course? This is mainly designed for quantum condensed matter people, with some more general things at the beginning for everybody. And so, anybody who is interested in condensed matter physics and related to condensed matter physics and use condensed matter physics, and also nowadays condensed matter physics is overwhelmed with topological phases and its manifestation in the electronic structure and experiments. So, one of the reason, I mean, topological phase, this course was not part of a main curriculum about 15 years ago, but if you look at the amount of research that has been done in last 15 to 20 years, it is overwhelmingly large. So, now this such course almost become a part of a curriculum, if not part of a given curriculum in an institute, but now through NPTEL and other exposures, you almost cannot escape learning it. Okay. And why this field has sort of expanded so much in such a short span of time? That is primarily because the topological phases of matter does not require interactions, and interaction, electron-electron interaction is something that is very difficult to model and understand, and there are a lot of bottlenecks in that field, but topology does not require an interactions. It pretty much comes from non-interacting electrons theory, and that is why the topological phases of matter can be computed from low energy model, tight binding model, as well as with density functional theory. And also experimentally, there is a lot of manifestation of topological phases, including its direct observations through edge states, boundary modes, as we can visualize in spectroscopies, as well as a lot of transport measurements, Hall effect and so on, anti-localizations, negative magnetic resistance. And also nowadays the field has even expanded into more experimental phenomena such as nonlinear effect, diode effect, Berry diode, optical spectra and so on. Okay. And we will almost talk about most of them, if not all. And those who are sort of in senior undergraduate students, it is probably a right time for them to look to study this course, and master students, PhD students and more senior even early career faculties would also benefit from this course. The prerequisites are that quantum mechanics 1, we anticipate that you have learned it, but we do not need quantum mechanics 2 for this course, and mathematical methods of physics is required. especially the vector space, Hilbert space, partial derivative and partial differential equation, and complex analysis, but not necessarily special functions so much, and also condensed matter 1, block theory, Fermi surface, Brillouin zone and so on, and condensed matter 2 is not required. On the other hand, few topics from condensed matter 2 or even quantum mechanics 2 will assume that you know, especially when it comes to defining model Hamiltonians and symmetries. So, second quantization is something you need to brush it up, and linear response theory or Kubo formula. But Boltzmann transport also, if you can go through, and Rode model, that will be beneficial. Okay. So, these are the references, and not so many book has come up, at least in recent time there had been few books, but earlier there were not many books, but there were a lot of research articles and review articles. So, pretty much the first book was this one, and after that also a lot of development has happened, and this books cover some of them, and I will also cover many which are not part of these books. And if you want a more mathematical foundations, which will be my first chapter, it comes from this book Nakahara, and I would suggest you first go through my first my lecture, the first chapter of my lecture, then you can look back to this book, because this book is mathematically heavier than my lectures would be, in which what I will do is that I will try to go through the things in a more physics perspective. Then you should be able to connect to what mathematicians' language is. And in terms of materials and the band structure theory, so this was one of them, which is a colloquium article about topological band theory, and there are also classics about topological insulators and superconductors in these review articles. Okay. And this is the plan of this course, and it is a 12-week course, and every week is split into complementary topics, but obviously there will be little bit of spillover from one week to another week, and we will adjust as we go along. Okay. In the first week, I will try to give the more mathematical foundations of topology and geometry, and as I alluded earlier in my introductions, is that topology is a field that comes more from a mathematics, pretty much from where the how the general theory of relativity, in which Einstein was trying to develop how to write a physical laws in curved space time. Then he had to define many things, including connections, curvatures and all, which we will go through. And then gauge theory came. It also played an important role in the topology, Chern-Simons theorem, and later on it also found places in many other branches, in soft matter, vortices and all, and then I guess through quantum Hall effect and some more related phenomena around that time, through which the topology will enter into condensed matter. So, I will go through those backgrounds, but I will try to, and this itself is a full course. You will find it in books as well as in many other lectures that there are full course about this topic, which I will try to wrap it up in one chapter. So, what I will do is that I will try to go at a higher speed than I should, but what you have to do is that, and this is just pretty much most of the things will be re-derived later in all the other chapters, but this will give you a more foundations about where all these things concepts coming from. So, what we have to do is that you have to rewind the video or even stop and make your notes for this one, for this chapter. For the remaining one I will go through slowly, and in the second chapter I will talk about topologies with magnetic field, which is Aharonov-Bohm effect, quantum Hall effect, and This is a 4% name which I will introduce later. It is one of the topological invariant. And then we will move on to the topology without magnetic field, which are the Berry phase, topological invariants, band topology, topological insulators, semi-metals. There are many types of semi-metals. And then we will take model Hamiltonians. Along those also we will introduce more concepts, winding number, Chern number and all. So, we will start with 1D, and also we will talk about topological superconductors and Majorana fermions. Then we will go to 2D, and we will talk about Chern insulators, graphene, Halden model. And then we will spend a lot of time about symmetry. What it turns out is that symmetry plays an important role in classifying topological invariants and also plays an important role in getting topological systems, especially chiral symmetry, time reversal symmetry and parity, inverse and then so on. So, this chapter is pretty complementary to this, put all of them. So, you can even start this one at any time before even taking the remaining chapters, or even at this point also anytime. Okay. And here I will mainly be focusing about discrete symmetries and how these symmetries manifest in second quantizations. This will be my focus. And then we will talk about time reversal symmetry, Cramer's degeneracy and how that leads to new types of topological phases. And in this chapter we talk about topology is defined in a periodic boundary condition, and once you lose that periodic boundary condition, you cut it at the edge. There are consequences, there are polarizations, surface states, localizations, and we will talk about those boundary states. And now we see a lot of papers and experimental manifestation also of quantum geometry, quantum metric and curvatures, which appears in low energy theory and correlation effect, putting bounds on many correlation effects and superconductivity, and as well as in flat band physics. So, we will spend some time on this, and then the last 2 weeks we will talk about many experiments, spectroscopies, transport, and we will also talk about nonlinear effects. Okay. So, with this overview of the course, let me start with the first chapter. All right. So, as I said, the first chapter will be mathematical foundations. So, this will be more of a mathematics about topology and geometry, and I will also touch upon the relevant physical properties as they appear, but most of the physical properties will be derived in the subsequent chapters. And we will go at a higher speed than it I should be, but you have to slow it down or rewind to go through any of the points that you miss out. Okay. And also some of the derivations I will skip and I will do it little more schematically, and those who will be interested in going into the details of those can look into Nakahara book, and also there is a book by Nash and Sen, which I did not put there, that also you can look at it, and the other one is Nakahara. These 2 books. Okay. All right. So, this is the plan for this week and for this chapter. So, one good thing about most of the mathematical methods, mathematical foundations of most of the things we study can actually start from set, and set is something that we have studied in high school. So, I will start with set and build up all the remaining ones. So, the first few things I will just take it as a reminder to what you are what you have what you know, or you can brush it off. So, I will just go through it very quickly. Set, equivalence class, equivalence relations, map, And these two also I will assume that you know, which are that once we start adding things on set, set is any set in which you just have elements, points, numbers and all, you can just put them together and define a set. But once you start adding things on set, some structure, some properties, then we start calling them differently, and we define vector space by adding closure property on sets, and the same thing in a different way for group, and I will go through those quickly. Then we will come to topological space, in which what you do is that set is there is no arrangement about the numbers or the elements of a set, but once we start making arrangement and we give a rules of how to arrange those numbers, and if you change the arrangement how things are supposed to change, this is how a topological space arises. And as we have different space, whether it is vector space, groups, topological space, for everything one should be able to go from one such set with that structure to another set with the same structure, and for each such set there has to be map. If the map keeps the set with the structure with another set with the same structure, then we will call them as morphism. Okay. So, for topological space, if you have a map that preserves the topology, we will call it continuous map and homeomorphism. And then to define any equation of motions and how the particles are moving in a topological space and all, we have to first define curve, then homotopy group, which will also help us figuring out how to dissect different topological space and what are the things that quantify or identify a given topological space, which we will call topological invariants. And then we will move on to define manifolds. Okay. So, manifold, roughly speaking, a topological space which is an abstract space we made of some a set of points, but a topological space in which we can coordinatize at least locally, we can define a local coordinate is roughly speaking what we will call manifold, and we will introduce the mathematical definition and the maps, differentiable map, diffeomorphism between two manifolds, and then eventually we will spend quite a bit of time about defining calculus on abstract manifold and the directional derivative and how they are done with tangent space and dual space to define the vectors, and so vectors will be defined on a tangent space, and then you need dual space to define the length of a vector or the inner product, and then we will go to fiber, because for eventually for us we do have a parameter space like Brillouin zone, like phase space or even real space. But at every point we have some wave functions or some spin vector or some other vector field and all, and how they are changing as the particle moves. This is essentially what we will be studying in quantum mechanics and so on, and this additional space we are putting at every point on a manifold together we will call it bundle. And we will also have fiber bundle, and principal bundles is roughly what we will be focusing on this course, in which we have the wave functions at different or rather a group at a different point on a manifold. And then we want to do a derivative on that fiber, on that vector space, on that fiber bundle, which is called covariant derivative, and through which we will introduce connection, parallel transport, curvature, and we will make connections to Berry phase, Berry connection, Berry curvature, and so on. Okay. So, I am assuming that set you know. So, this is just a reminder. Okay. So, set is a collection of elements, call it A and B, and we denote it generally like this with curly bracket A, B, which are the elements, and with a bar after the bar we put any conditions on those elements, okay, and we denote it like this: A belongs, the small a belongs to capital A with this symbol. It is an element of this set, and conditions will be on this. We can combine two sets, and this is called union of a set, in which we take the elements from both. You can have an intersection which is also a set that takes only those elements which are present on both, and then a subset will be some subset of a bigger. So, let us say I have some bigger set, and any subset will be like this, okay. And complement of a set will be, again I have two sets and I remove the elements which are there in y and x, and if I remove those elements which are in y from x, the remaining elements form also a set, and that is the complement set, residual set. Okay. So, Cartesian product between two sets is slightly different from the general product, and I want your attention is that. So, let us say I have two sets A and B, and with being the elements A1, A2, B1, B2 and so on, and the Cartesian product is each element of the first one is multiplied with each elements of the second one. So, you take the first element A1, multiply with B1, B2, B3, and here are only two of them. And then you take B2, and then again you multiply with B1, B2. So, if I draw like this, so this is my A which has two elements, this is my B which is two elements. So, now I will have multiply this element with both the elements, or rather let us do it R. So, R is a set of real numbers. So, I have all the numbers here, and I multiply with another R set, that is also a real number. So, now at every number of this R, I multiply all the numbers of the second R, and I do that. So, this sort of covers your all elements in a 2 dimensions from minus infinity to plus infinity, and this will be called R2, which is a R Cartesian product with R. Okay. And these are the common sets we use. So, R plus is positive real number, this C tells you the complex number. So, R D is a D times D dimensional space. So, it is a Cartesian product of D R sets. S1 is a circle. So, it is made of two elements, but with a constraint. It is only the elements on a given radius is different. So, it is actually made of one element, one can even define it with theta, an element where the theta will go from 0 to 2 pi. Z is a set of all integers, and Z2 is a set of two elements, and being minus 1 plus 1, 0 1, they are all isomorphic. Equivalence class or equivalence relations. So, it turns out is that in sometimes if I have a set in which I have, let us say, many elements, let us say this is my some set and many element, but not all elements are completely independent. There are certain set of elements which are sort of related to each other, then you have another set of elements which are related to each other. So, then one does not need to work with such a big set, one can even define a smaller set which we will call equivalence class. And how do you define it? Let us take an example. Let us say I have a set made of triangles as being the elements and squares Let us put circles. And there is no ordering, right. If you just rearrange them, the elements how they are where you put them in a set, it does not really matter, right. So, now we see that there are at least two different types of relations we can write between some of the elements. For example, these triangles are related to this, these triangles are related to this. So, these elements has some relations among them, and then these squares are related to this, the squares are related to this, and also then the circles are related to each other. Okay. So, they are related with this. So, we sort of found one relation which is by shape. One can also come back and define relations between different colors. Here I have chosen the same shape with same color, but one could have started with different colors for the same shape, and then one could have even defined relations between the same color rather than being between different shapes, and one could also come up with another relations. But not all such relations will qualify or will accept it. The relations that follows these axioms, the reflectivity, the two elements, each elements are related to each other, of course, and if A is related to B, B is also related to A. So, A is related to B, B is related to A, kind of symmetric and also transitive. So, if A is related to B and B is related to C, then A and C are also related by the same relations, and we denote this symbol as a relations. Okay. Now, what we can do is that now because we do have a relations between some of the elements, one can actually define a smaller set which is called quotient space. So, how do you do that? We take all these elements which are related to each other and define a class which will be defined by square bracket. So, this is one class, and let us say here this is one class which so we can write it. So, this is one class, and then you have and we define the other one also. So, this is my class and this is my, and this is going to be my class circle. Now, see that because all the elements of a class are related to each other, we can just define a class with just one element, and you can take these classes, 3 classes, and define a smaller set. Okay. Okay, let me start with this. And we call it a set which has 3 elements. Okay. And this one is the quotient space. So, we started with A and now we define a smaller set and we denote it by. So, we removed all the elements, all the redundant elements which are related to the remaining elements by the equivalence relations. So, it is kind of a complementary set if you like, and the elements we have removed are actually not any arbitrary elements that we have removed, but the elements which are related to the elements we have already included, that is called the quotient space. Okay. And some examples of the quotient spaces are something that we use often. So, Z is a set of integer, and we can divide it into odd and even equivalent classes, and then if we remove those equivalent classes and take only one element from each equivalent classes is what is included in a quotient space, right. So, if I take the quotient with this equivalent class, that odd numbers and even numbers, so we are only left with only a set of two numbers. So, it is a Z2 group. The quotient space of Z under the even and odd is 1. So, circle is a quotient space of R under the relations that y and x are related to each other if they are on a circle, okay, or under a periodic boundary condition. Okay. So, let us say I have some line, all the points in a line, and which is my R, and now I put a periodic boundary condition saying that all the points within this region defined by length L A and every other point here are related to the point, and every other point here is y are related to the points which are in x in this set defined from let us say 0 to A. All the points outside this set A are related to A by a translation of y being equal to x plus A. So, that is the periodic boundary condition we see in a unit cell in condensed matter physics. So, that means we can just work with this smaller unit cell, this few points, and we do not need to work with the rest of it, and that is how a Brillouin zone or unit cell is created. We can just work with one unit cell and every other unit cell are just periodically translated. Okay. And if you do the same thing in 2 dimension, and so this is this point and this point are also same, they are translated by a lattice vector. So, then this point and this point are same. So, we can actually even draw a line. So, I started with the first point and all the other points, and then I do that, and this is S1. So, R under this equivalence class in which put a periodic boundary condition is isomorphic to S. Okay. And if you do the same thing about along two x and y directions, we put a periodic boundary condition along both directions. So, you have a S1 Cartesian product with S1, and that is a 2D Brillouin zone which is torus. This is the this is the notation for a set torus. Okay. And then we talk about map. So, map is a map that takes you from one set to another set. There will be 3 types of maps, but let us just start with the definition of map. It is often denoted, or it is always denoted by this notation. So, F is the map with a colon that takes you from one set to another set, and the first set from where you start is called domain, and the set that you go to the final set is called range or codomain x and y. And elements wise, so you take any element x, and under this map F you get Fx, it gives you a rule, kind of a function if you like, and that must be in the y set. That is how the map is, right. So, these are the elements of it. So, it is f of 2 gives you B. So, x belongs to capital X set and y must belong to set B. So, f x is this one is called the image of x in set y under the map F. It is called image. We will talk about inverse, but let us talk about the pre-image. Pre-image exists even if the is a notion even when the inverse does not exist. So, what it is that suppose I start with some element in the range or codomain state B. So, it tells you where, so it is mapped from set X, but which element mapped. It can be more than one element mapped to the same node. So, that is called all the elements that map to this element is called the pre-image of B, and in this case the pre-image of B is 2, but you can have many more elements, all can map to a given element and all of them will be called pre-image. This is a notion that will be useful. So, there are 3 types of maps we talk about: injective, which is that all elements of your domain is mapped, but the range may have more elements which is not mapped. Surjective is the opposite, all elements of the range has to be mapped. It can be mapped by multiple elements from your domain, surjective. And bijective is when all elements are mapped to all elements, and so this means every element. So, it is a 1 to 1, all elements are mapped to a single element. That is the bijective map and that is the map that we will be using. So, when you have a bijective map, then obviously you can always go this way and this way uniquely, right. So, that means the maps are invertible. So, if f takes you from x to y, then f inverse, the inverse map takes you from y to x, where they are denoted like this. So, y is mapped to f inverse y, which is equal to x. So, if a bijective map exists between between sets x and y, they are called isomorphic and denoted by this symbol. This is not a random symbol, this is actually a mathematical symbol which tells you that this set x and y are isomorphic, 1 to 1. We do not use this symbol for surjective and injective map, it is only defined for bijective map. The kernel is a concept that we may not use much, but let me just remind you what it is. Kernel of a map is a subset of the domain X whose all elements are mapped to 0. So, let us say I put some 0 element here, kind of null element if you like. All the element that is mapped to there, it is under this map F is called the kernel. Okay, that is defined as it is. Now, composition of 2 maps. Let us say I go from x to y with one map and then y to z another set with another map, and I should also be able to go directly from here to there, right. How do we do that? We compose those 2 maps, and generally we denote by this abstract symbol O, and for specific cases one has to define what they are. So, here it is like x goes to y with f and y goes to z by g. So, the composed map f after g, and I will talk about that thing again, sorry, g after f, which should take you from x to z. This is a map which will take you from here to there directly, and sort of denoted like this. So, it is a composed map acting on x, what it should give? It should give z, and we can also denote it like this. So, f is a function of x and g is a function of f x, it should take you to an element in z. So, it is sort of read at g after f, because f has to be operated first, which it acts on the domain set, right, and then g has to be operated, they do not go in the reverse way. This is the composition operation, and F and G commute, then obviously G and F is continuous. And order do matter, as I said, that is why we call it G after F. All right, gave you a quick summary about set and the map, and now we are going to add things on the set and we will get different things. And again, vector space and group is something that I am assuming that you know, which are defined with some closure property. And before I then I will talk about the topological space in which we put a topology in the set. Okay. So, we will start these things in the next class.